Hello everyone. First of all, thanks for attending this talk. I'm Ángel Palomares from University of Granada, Spain, and in this talk I will present our work entitled Reconfigurable Phase Shifter in waveguide technology based on Glide-Symmetric Holey Structure. In this work we mainly explore the potential of the Glide-Symmetric Holey Structure in rectangular waveguide in order to take advantage of them in the design of a reconfigurable phase shifter. This is the outline that I'm going to follow. First, I will do an introduction about the application that have the implementation of periodic structure in waveguide. Besides, I will introduce the glide symmetry and recent works that apply this higher symmetry to enhance or create the desired performance of the devices. In the second point, I will talk about the specific structures selected in this work and why they offer an advantage. Additionally, I will show how their dispersive characteristics change with the modification of the geometrical parameters of the unit cell and the implementation of the through-hole in the structure. Then, in the third point, we take advantage of the Glide-Symmetric Holey unit cells and the through-holes to design a reconfigurable phase shifter. The design is analyzed in CST and some results will be presented. Finally, the main conclusion of this work are commented in this last point. Waveguide technology is one of the preferred guiding structures for electromagnetic waves in higher frequency due to its inherent low losses regarding traditional technology such as microstrip. Therefore, there is a need to use this technology in the design of the devices at millimeter wave frequency. In addition, the manufacturing of the waveguide is relieved by gap waveguide technology that allows the cost-effective fabrication of the design in several layers. Some of the most used EVG structures in gap waveguide technology are bed of pins or Glide-Symmetric holes. One strategy to design a radiofrequency component such as filter or phase shifter in waveguide is the inclusion of periodic structure inside the waveguide. Here it is present some example of filter designs. For example, in 3, it is used vertical resonant loads in the vertical plane of the waveguide to create EVG structure. Or in 4, which is a SIW, is drilled in a periodic way. On the other hand, there are examples of phase shifters designed by periodic structure. The work in 6 use omega particle as periodic structure, or the work in 8 that employ tiny periodic pins to achieve the desired phase shift. Those periodic structures can enhance their performance by the use of glide symmetry. Glide symmetry is a type of higher symmetry that is composed by two geometrical operators, a mirroring and a translation of half of the period of the unit cell. Some advantages that present the use of glide symmetry are reduction of the dispersion over a wide frequency range or increase the phase constant of a periodic structure. Next, I show some of the work in the literature designed by periodic structures with glide symmetry. In all of them, a unit cell with glide symmetric configuration is used to achieve a specific goal. For example, the lens design in 9 uses a unit cell with glide symmetric configuration to make constant the equivalent reflective index over a wide frequency. Or the work in 11 uses a prince loaded with glide-symmetric holes to reduce the beam squint of a leaky wave antenna. All previous works include the glide-symmetric unit cell in a parallel plate waveguide. Alternatively, glide-symmetric unit cells can be employed in a rectangular waveguide. In this manner, these two works use glide-symmetric unit cell to create phase shifters in waveguide. The first uses a unit cell with glide-symmetric pins, as can be seen in the inset, and the other work employs glide-symmetric holes. To compare the performance of both unit cells, it is typical to employ the eigenmode solver to obtain their phase constant beta along the frequency. This figure shows the normalized phase constant along the frequency of both presented unit cells, and both are compared with the phase constant of a reference waveguide. It is observed that the blue line corresponding with the Holey unit cell is low dispersive compared with the reference, the black line. In other words, the phase constant difference between both unit cells is almost constant along wide frequency range, and in consequence, both lines are parallel to each other. The translation of this fact to the design of the phase shifter is that the phase shift produced by the Holey unit cell will be constant in frequency, while the phase shift produced by the unit cells with pins will not be constant as the frequency changes. In this second point of the presentation, I will enter in more detail about the Holey unit cells, and I will show the selected Holey unit cell for the proposed reconfigurable phase shifter. First, we consider a rectangular waveguide where the propagation direction is in x direction. Its height is not standard, but its width is standard corresponding to WR15. The width of the waveguide fixes the cutoff frequency for the fundamental mode. The complete waveguide can be viewed as a concatenation of waveguide of length p. If we load the top and bottom parts of the waveguide with symmetric holes, as it is shown in this figure, we obtain mirror symmetric Holey waveguide, and it is mirrored because the top and bottom holes are symmetric regarding the xy plane. In this case, the unit cell is composed by waveguide loaded with 2 holes at the top and 2 holes at the bottom. Another interesting configuration of the holes is illustrated in this figure, where the bottom holes have been displaced half of the period in the x direction. Now the holes preserve glide symmetry, and the stop bands disappear, as can be seen in these regions. Therefore, to ensure a wide band performance, the selected Holey waveguide is the one with glide-symmetric configuration in its unit cell. In order to observe the influence of the geometrical parameters in the dispersion behavior of the glide-symmetric unit cell, dispersion diagrams are computed when the hole radius and the hole depth are modified. Comparing the effects of both parameters in the dispersion diagrams, first detail that can be appreciated is that both radius and depth of the holes produce a Holey unit cell denser when they increase. Regarding the mode 1, the fundamental mode, it goes lower as this parameter increases. It is important to note that the modification of the parameter is still preserving the parallel behavior. Second detail observed in the dispersion diagram is that the hole radius produces greater change in the mode 1 position. On the other hand, the effect of the hole depth is limited, and the mode 1 cannot be pushed to lower position in the dispersion diagram up to certain value of the hole depth. In this slide, we consider several Holey glide-symmetric unit cells that form a Holey waveguide. If we observe the electric field distribution inside the Holey waveguide at this cutting plane, we obtain this view of the electric field. We see that much of the electric field is in the waveguide, but there is part of the electric field that enters into the holes. However, it is also appreciated that the electric field inside the hole is not extended up to the end of the hole, and this is because the fields inside the holes are in cutoff due to the dimension of the holes and the operating frequency range. And also, this is the reason why the depth of the hole has a limited effect in the dispersion diagram commented in the previous slide. This fact can be taken in advantage to do through holes, instead of hole as it is presented in this figure. No modification existed in the behavior of the electric field compared with the case of the hole with metal at their bottom. This comparison is true when the depth of the hole is bigger. And this supposes an advantage because can be introduced element inside the holes, and these elements can be controlled outside the waveguide. Now, knowing this advantage, we focus our attention in the hole depth of the Glide-Symmetric unit cell. Employing the agent mode solver, we represent in more detail the dispersion diagram when the hole depth increases. As previously said, the fundamental mode of the Holey unit cells move to the right, modifying the phase constant but preserving the parallel behavior regarding the referent, which is a rectangular waveguide. This information provided by the dispersion diagram can be translated in phase shift of the Holey unit cell regarding the phase produced by the reference waveguide. In this plot, it is represented the produced phase shift of the Holey unit cell when the hole depth increases. As it is expected, the greater the depth, the greater the phase shift produced, but up to certain value that depends on the other geometrical parameters of the Holey unit cell. In this third point, I saw an example of reconfigurable waveguide phase shifter based on the through holes previously presented. Here it is the Holey waveguide, and the selected reconfigurable elements to tune the depth of the holes are screws with planar bottom. For this design, it is used 10 Glide-Symmetric Holey unit cells to achieve a 90 degrees reconfigurable phase shifter. These are the bottom and top views of the design, and here they are the values of the parameters selected. The hole depth of the Holey unit cells modify depending the position of the screw. In this cutting view of the design, it is clearly observed that the through holes are presented in the unit cell, and they allow the introduction of the screws, which fix the height of the holes. The width of the waveguide is the same as the waveguide standard WR15, so the frequency range is from 50 to 75 GHz. The height of the waveguide is smaller than the standard, so transition to a standard rectangular waveguide is needed in a real implementation. It is important to note that only Glide-symmetric configuration of the through holes avoid the stop bands, and in consequence, the operation is in the maximum bandwidth. In order to avoid propagation inside the hole when the screw fixes a small depth value, there must be a perfect fit between hole and screw, because otherwise there exists a coaxial mode along the screw that modify the behavior of the phase shifter and allow resonance. Finally, since the depth of the holes are reconfigurable, other non-Glide symmetric configuration can be set providing stop band behavior, and in consequence, the waveguide can produce filter behavior. Here in this slide, it is illustrated the electric field distribution for different screw positions. First, it is shown when the screws set a hole depth of 0 mm. In other words, it is the reference position and the waveguide without holes. Observing the electric field distribution from a top view, at the output port is obtained a phase of phi. When the screws move upwards, the consequence is that the wave represented by its electric field distribution is shifted 45 degrees compared with the reference position. Finally, if the screws move upwards to their limit position when the depth of hole is 1 mm, the phase shift is increased up to 90 degrees. These electric fields are at one frequency, but if we represent the obtained phase shift along the frequency, we observe a planar response in all the screw positions, and it is due to the parallel behavior of the Holey Glide-symmetric unit cell compared with the reference waveguide. Also, it is shown the S parameter in magnitude. illustrating very low reflection coefficient for all the position of the reconfigurable phase shifter. It also provides a good point to the performance of the phase shifter because no matching structure are needed in the modification of the hole depth. In this final slide of the presentation, the conclusions are enumerated. The most important conclusion of this work is that a wideband 90-degree reconfigurable phase shifter is obtained thanks to the use of Holey Glide-Symmetric unit cells based on through holes where reconfigurable elements can be inserted. These are the references used in this presentation. And finally, thanks for watching this presentation.